Hello all, as we continue to look at the definitions of sine, cos and tan. In our part 1 of exercise 6b video, we looked at the definitions of them and how we could quite easily find what sine, cos and tan would be of angles related to 0 degrees, 90 degrees, 180, 270 and 360 and the radian equivalents of those. They were pretty easy. We could work on them logically by just thinking what's the x component, what's the y component, or how long would the tangent be. We're now going to look at some other values, some exact values or answers to some angles that are in between there, some ones that are going to come up a lot. They are 30 degrees, 45 degrees, and 60 degrees, or written as radians, pi on 6, pi on 4, pi on 3. And I'd really suggest you just get used to working in radians, because pretty much everything we're going to be doing from here on out is probably 90% of it's going to be in radians. So you've got to remember pi on 6 is 30, pi on 4 is 45, pi on 3 is 60. This table, just copy it down now. Put it in your reference book, copy it down now, but you're also going to have to memorize it. Now, like I said, for 0 and 90 or pi on 2, you can work logically. You can, even if you forget these, you can work logically to figure out what those are. The 30, 45, and 60 in between, they're a little bit harder. But we will show you a way on how to remember these. Now, the thing to note for sine and cos is that all of them are divided by 2. Everything is a fraction. Divide by 2. From there, the numbers just go up, then go down. So the numbers go 1, 2, 3. And you could even think that this is the square root of 1, and same down here, we could think that's the square root of 1. So we can always set up the sine or cos, we can set up square root something on 2. Now, how do we know if it's the 1, 2, or 3, or the 3, 2, or 1? Well, some people, what they do is they remember how to build the table, and at the very start of the test or SAC, the very first thing they do is they write down the table. And the trick here, as it says, okay, for sine, the numerators count up. Okay? They go up, 1, 2, 3, up, and then for cos, the numerators go down, 3, 2, 1, down. Again, though, we can work at this logically. Let's think of the unit circle, and as we go round, what happens to the y value? Well, it starts small, it gets bigger, it gets bigger, it gets bigger. Therefore, our number or our fraction should get bigger. So it makes sense that 1, then 2, then 3 for sine. As the angle gets bigger, heading towards 90 degrees, once we go past 90 degrees, it actually starts coming down again. But going between 0 to 90, as the angle increases, the y component increases, so our fraction should get bigger. So it makes sense that we have 1, then 2, then 3. And we can think of the exact opposite for cos, which is the x component. It starts really long, and then it gets smaller, 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 getting towards 0. So our fraction should get smaller and smaller and smaller. So our numerator should get smaller, smaller, smaller. So that's the way that we can go about trying to remember that. A mix of memory, remembering it's always the form of square root on 2. Now, what number you put inside the square root changes. It could be a 1, it could be a 2, or it could be a 3, and square root of 1 just becomes 1. So you can simplify that to half. Same over here, simplify that to half. The other ones just stay as. Now, tan's a little bit trickier. Tan of 30 degrees is 1 on root 3. Tan of 45, we've already talked about, is 1. And then tan of 60 is root 3. One way that I've seen people remember it is just remember tan of 30 is 1 on root 3. And then it gets split up into the 45 and the 60. The 1 becomes 45, and the root 3 becomes the 60. Again, logically, you'll notice these numbers are becoming larger. As we go around, our tangent is small, our tangent gets bigger, our tangent gets bigger. So that's another way. If you can remember, one is 1 on root 3, and another one is root 3. What order they go in? Well, smallest one is 30, middle 45, largest is 60 degrees. This 1 on root 3 can also, and you'll see it very often, they'll actually rationalize the denominator. This can actually become root 3 on 3. That's the same thing. But either one of those will suffice for now, but we'll get in the habit towards you don't want to leave a third in the denominator. You want to rationalize that. And of course, tan of 90 is undefined. But that's how we go about remembering all these exact values, because most of the time we're going to be answering questions as an exact number, not as a decimal estimate. Rightio. Some symmetry to do with values. If we have some angle, okay, we've already looked at in our previous video, but sine is going to be positive in quadrant 1 and quadrant 2 for sine. So let's maybe make up a little key here. We might go sine, 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 cos, and tan. So it just so happens that sine in quadrant 1 and 2, our y values are positive. In quadrants 3 and 4, they're negative. Cos, positive in quadrants 1 and 4 because it's the x coordinate, and that's positive on that side, but they are negative in quadrants 2 and 3. And then tan, and we can get our sine for tan thinking it's the other two divided by each other. So what happens with the sines? Well, positive divided by positive in quadrant 1, positive. Negative divided by positive is a negative, of course. Negative divided by negative makes tan positive in quadrant 3. Tan is the only thing that's positive in quadrant 3. And then tangent, negative divided by positive will also be negative in quadrant 4. So there's a little bit of a table to help give you a quick reminder about when are they positive, when are they negative. Now, a quick look at symmetry, and that's what these boxes over here are giving a hint towards, is that doesn't matter what quadrant we're in, we can always think of that angle in terms of the first quadrant. Okay, there's a matching angle in the first quadrant where we would just have to adjust the sign. So let's look at 3 pi on 4. As we come round over to here, this would be 3 pi on 4. And if we want sine of that, well, sine is the y component we've talked about coming through. So 3 pi on 4 would be the exact same as some other angle coming up this way in the first quadrant. The y component of it would be exactly the same. Now, what is this angle here? Okay. Or we might call it alpha. What is that angle there? Well, that alpha angle there would be the exact same as alpha on that side, which is actually equal to pi take away our original angle. So theta is our original angle, so alpha is going to be equal to pi. So imagine going all the way around to 180 degrees, then take away our original, take away our 3 pi on 4. That gives us alpha here in the first quadrant. And so if we can find what it is in the first quadrant and then just think about what sign it needs to be, that will be really handy. So how would I write this out? Well, sine of 3 pi on 4 would be the same as sine of pi take away 3 pi on 4, which we can write as sine of pi on 4. Okay, so sine of pi on 4 will give me the answer to my original question. They are equivalent. Do I need to change the sign at all? No, I don't, because in quadrant 2 it is still positive. We can do this exact same thing for cos as well, and tan. Just think of what would be the equivalent angle in the first quadrant. That would give me the same x component. So let's do cos of let's go 7 pi on 6. We're going to do cos of 7 pi on 6. Well, that's greater than a single pi, so we know that's going to be coming around here, and it actually happens to be like that. Now, cos is the x component. So that all the way around to there, that was theta is equal to 7 pi on 6. Now, the x component is this distance along here, would be the exact same as another angle. We call that alpha just in that bit. Call that alpha there. That line there matches that line there. They're both the same. What is this angle alpha? Well, if we think to get to this 7 pi on 6, I've gone all the way around to pi, which is the same as 6 pi on 6, and then I've gone another pi on 6 to get to there. So over here, this angle here would be pi on 6. Or we can look at it. We would want to try and rewrite this 7 pi on 6. We want to try and rewrite it as I've got these signs a little mixed up. I really should be writing that as theta and this is our alpha. We want to try and rewrite our original angle, theta, which we had in terms of pi plus something. So 7 pi on 6, we can write that as cos 6 pi on 6 plus another pi on 6, because 6 pi on 6 is the same as pi plus pi on 6. So this is now telling me what my equivalent angle, this one here I can read, that's my equivalent angle in the first quadrant, which we showed geometrically was pi on 6. Okay. Now, cos of pi on 6, if you think back to that table on the previous slide, that is equal to pi on 6, that's a small angle cos, x component would have a large, small angle creates a large x component, so that would be root 3 on 2. The only thing here is we're down in quadrant 3. Is the x component technically of quadrant 3 positive or negative? In this where we need to just think logically. That is the same as, so the answer would be negative root 3 on 2. So that's how we can use symmetry in thinking of where is my angle, how can I convert it back to the first quadrant. What's the equivalent angle in the first quadrant? That would give me the same x or y component. And then we just need to think about what, well, is that x or y component actually positive or negative from my original angle? So that's what all of that there is trying to show. I apologize for the mix up in the slides, but the trick is whatever it may be, it might be cos, you'll have some original angle. You're going to try and rewrite it for quadrant 2. You're going to try and rewrite it as cos pi take away some other angle, and this some other angle is what you actually get to use in quadrant 1. Use that in quadrant 1 and then just figure out if it's actually positive or negative for your original quadrant. Same for quadrant 3. We would have cos of theta. You want to try and rewrite that as cos of pi plus some angle, and that some angle, that's what you can use in quadrant 1. Quadrant 4, same thing, cos of whatever angle that got you in quadrant 4. We try and rewrite that as 2 pi take away some angle. Okay. And again, that something is what you can use in quadrant 1, and then just figure out if it's positive or negative. And you can do that the same for sine and tan. That's going to hold for all 4 quadrants, sine or tan. I could change this to sine and sine there. Completely fine. So that's how we go about dealing with work in quadrant 2, 3, and 4. Find the equivalent angle in quadrant 1. Here's some examples. I'm only going to do a couple of them because this video is getting long and this is already part 2 of exercise 6B. So sine of 45, well, that's pretty straightforward. That is going to be root 2 on 2. cos of 60 degrees, remembering off the table, cos of 60 degrees, that's asking for the x component. Just to talk you through it, cos 60 degrees is going to have a small x component, so that would be the same as half is the smallest one. Tan of 30, well, we know tan of 30 is 1 on root 3. Right, so now let's go about this. Cos 150, we know that's in the second quadrant. So I'm going to try and rewrite that as cos of 180, take away something. And it's obvious that that something is equal to 30 degrees. Now, since I've written as that, I can now actually say that's the same as cos of 30 degrees or something. And then I just need to think, was my original quadrant, cos of 150, is that positive or negative? Well, over 150 over here, cos is asking for my x value, so that's actually negative. So I need to put negative. So now it's just asking, the answer is, what's cos of 30, and then make it negative. We know cos of 30 is x component, that'll be large, so that's root 3 on 2, and I just need to make it negative. Tan of 210, I want to write that. 210 is over down in here in the third quadrant, so I want to write that in terms of 180 plus something. And 210 is obviously 30, so I can say that's equal to tan of 30. Now, is tan positive or negative in the third quadrant? It is positive, so I can just leave it as positive. And tan of 30, we already know from up here, is 1 on root 3. So we can do that. Sine of 315 degrees, we need to think where that is. That is, of course, sort of over here. So I want to try and write that as sine of 360 take away some angle. Now that would need to be 45 by something. So I can rewrite this as sine of 45. And is it positive or negative when we think of in terms of my original quadrant? Well, sine is asking for the y component, and the y component down there is negative. So I convert it to that. Sine of 45 is root 2 on 2. And I just write it as negative. Same thing for GH and I. Just now in radians instead. 5 pi on 3. Well, that is 5 pi on 3 is around there. Yeah, because that's like 1 and 2/3 pi. Yeah, so that's going to be around in that quadrant. So I want to try and write this as sine of 2 pi, take away something. And that's going to be take away 1/3. So I can write that as tan of 1/3. Now thinking back to my original quadrant, tan down here in quadrant 4, that is negative, so I need to put a negative sign there. And tan of, I left out the pi, that should be pi on 3. Pi on 3, tan of pi on 3, and if we remember, pi on 3 is 45 degrees, if that helps you at all. So that is equal to -1. Sine of 5 pi on 4, well, we can write that as sine of pi. It's going to be in this quadrant here, pi. No, it's not. Is pi plus something. Is pi plus pi on 4. So I can rewrite that as sine as pi on 4. And was my original quadrant, is it negative or positive? Well, my original quadrant's down in quadrant 3. I want the y coordinate, it's going down, so therefore it must be negative. And sine of pi on 4 is root 2 on 2. and we just make it negative. Cos 11 pi on 6, well, that's almost 2 pi because 12 pi on 6 would be 2 pi. So that's clearly going all the way around to almost over there. So I can write that as cos of 2 pi take away something in quadrant, and that's just going to be take away pi on 6. So I can rewrite this as cos of pi on 6, and think about my original value. I wanted the x coordinate because it's cos, and the x coordinate is going to be positive, so I can just leave it as positive. Cos of pi on 6 is going to be quite large, because small angle for cos means a large x component. So that would be the root 3 on 2, and it's just going to be positive. The exact same thing can be applied for negative angles here in example 3. Think about how can I rewrite it all. Actually, no, sorry. Before I get confused. Sometimes we might have to work the other way around. Instead of being told the angle, we're told what the x or y component is, and we need to roughly estimate what the angle is. And that's what this is looking at here. So working backwards. So we're told sine of x, so some angle is going to give me a y component of 0.1. So if we thought in the first coordinate, that's going to be a really small angle. It's going to give me a y component of 0.1. What would be sine of pi take away x? What would be now what's the new y component? That's what it's asking. Sine. It's asking sine of something. What's the new y component? Well, if I went to pi and then just came back, whatever this angle x was, if I zoom in on this diagram, let's draw it bigger. I've gone some angle, it's given me a distance of 0.1 as my y coordinate. Now I'm going to go to all the way around to pi and then back that angle x. Now I've gone to pi, subtracted x, I've gone back up this way. That's what this bit here is saying. What is my new y component? Well, it's quite obvious that it's exactly the same, equal to 0.1. I could have also written this as equal to sine of, just realizing that we're at pi, negative x. In the second quadrant, this stays positive, so it's going to be equal to 0.1 as well. I can work that way. What happens if I went instead to, if I go to 2 pi and then take away x, whatever that angle x is. So I'm going all the way around to 2 pi, then I take away x, so I've gone to 2 pi. Now I've taken away x, what's going to be my y component? Well, it's pretty obvious that y component is going to be 0.1, and it's just going to be negative 0.1. So I could get 0.1. The other way I could have done it is looking at those patterns from the previous thing we worked on. Went, well, actually I can just write that as sine of x, and then just think about what quadrant am I in? Well, 2 pi take away something, I'm in quadrant 4, it's going to be negative, so I'm going to get negative 0.1. What happens if I go to 3 pi plus x? Well, 2 pi all the way around, go again another pi, then add x to there. What's my y component? 0.1, and since I'm going down, it's negative, so I get negative 0.1. I could have also just written this as sine of x, and because I'm in the third quadrant, it would need to be negative, which also gives me 0.1. I'll leave example 2 as a bit of a challenge to you. It's these very similar sort of thing, and we're just given a zone we need to be in. X needs to be between pi on 2 and pi, so my angle needs to be in this range. What angle will it be that gives me the same cos as negative cos pi on 6? Be over here. What angle do we need to get over there? And we can apply all the same stuff to negative values. Instead of going around anti-clockwise, we can go around clockwise as well, thinking logically. That's it. Another long video, my apologies, but if we get all of this down, it's going to make all the rest of it a lot easier if we're thinking geometrically about it. Let's sign Cosine Tanner. Have a good day, and that's it for me. Any questions, put in the comments below. Send me an email, put in Google Classroom, or ask in class.